Um, let's just follow up and finish our discussion about position, velocity, and acceleration functions. So these are the functions. And so what that means is when we look at the velocity function, it's negative 2 pi meters per second. So that means that these maximum values here are 2 pi meters per second. So 6.28 meters per second. It's oscillating between positive and negative 6.28 meters per second. So the maximum velocity is this value here, the absolute value of it. And for maximum acceleration, which is occurring when it's at its endpoints, it's fluctuating between positive and negative 2 pi squared meters per second squared. So that's what's happening there. So I think that as you guys are working on this, it'll get easier for you. But if I ask you to write a position function or a velocity function or an acceleration function, you just need to know A and omega, and then you just plug and chug into the formulas. So if I wanted to write the velocity function for this one, the velocity function would be negative AW, so 20 times 3.14, negative 62.8 centimeters per second times cosine of 3.14 t. That easy. And if I wanted to write the acceleration formula, it would be negative AW squared. So A is 20 times 3.14 times 3.14 because it's squared. So 197 would be negative 197 centimeters per second squared sine. Actually, I'm sorry, I messed this up. This one should be sine, and this one should be cosine. 3.14t. So I'm just using those generic functions. So the maximum velocity is oscillating between 62.8 centimeters per second, which is just AW. And the maximum acceleration is oscillating between positive and negative 197 centimeters per second squared, which is AW squared. All right, let's talk about pendulum. A pendulum is also an example of simple harmonic oscillator. And when it's at maximum displacement, it's at its farthest points, and it stops. So this is also where it has its greatest acceleration. And when it gets to where it was just be hanging normally, equilibrium, it's traveling at its maximum velocity. And we already know that conservation of energy works for this. When it's at its maximum points, it has PE that gets converted into KE and back into PE as it swings back and forth. The period of the pendulum is equal to 2 pi L over G. So if I wanted to know how long, let's say that what is the period of a 2 meter long pendulum Earth? So on Earth, it would just be 2 pi times the square root of 2 meters all over 9.8 meters per second squared, which is gravity. So if I put all that in, 2 divided by 9.8, take the square root of it, times 2 times pi, and I get 2.84. So it would have an answer of 2.84 seconds. And then if I wanted to find out how long it would have to be to have that same period on another planet, so I'm going to set that period equal to 2 pi square root of L all over half of T, which is 4.9 meters per second squared. So what I'm going to have to do is I'm going to have to do a little algebra. I have to get all the numbers on one side. 2.84 seconds divided by 2 pi equals the square root of L all over 4.9 meters per second squared. Then I'm going to square both sides. So this will be 2.84 seconds squared all over 4 pi squared equals L all over 4.9 meters per second squared. So I'm going to have to multiply 4.9 meters per second squared by both sides to get my L. So my L is going to be equal to 2.84 times 2.84 times 4.9 divided by 4 divided by pi divided by pi one more time. Looks like it would be 1.00 meter. 1 meter. All right, let's just do a couple of example problems. A needle makes 30 oscillations after it's lowered. Write the position, velocity, and acceleration functions. So remember, x is equal to a cosine of omega t. V is going to be equal to negative AW sine of omega t. And A is going to be equal to negative AW squared cosine of omega t. So A is going to be 4 centimeters for both of them. And omega is going to be whatever 2 pi is times F. Well, F is going to be 30 oscillations divided by 1.5. Which is going to be 20 hertz. And so this is going to be 2 pi times 20 hertz, which is going to be 40 pi radians per second. So this is going to be 4 centimeters or 0.04 meters times the cosine of 40 pi radians per second, t. And then this is going to be 0.04 times 40. 1.6, so 1.6 pi radians per second times the sine of 40 pi radians per second times t, and it's negative. And this is, I'm going to multiply this by omega one more time, so that's going to be 1.6 times 40, 64, negative 64 pi squared radians per second squared. Actually, this would be I'm sorry. It's not radians because that's an angular measurement, and we actually were measuring, multiplying meters by radians per second. The radians get dropped, and we keep the linear meters per second here and meters per second squared there, times the cosine of 40 pi radians per second t. Just like that. And how long does a pendulum have to be on Earth to have a period of 60 seconds? So we're going to have t equals 2 pi square root of L all over g. So t all over 4 over 2 pi equals the square root of L over g. And I'm going to square both sides. So that's going to be t squared all over 4 pi squared equals L over g. So L is going to be g times t squared all over 4 pi squared. And so we want it to have a period of seconds. So 9.8 meters per second squared times 60 seconds squared all over 4 times pi squared. 9.8 times 60 equals, divided by 4, divided by pi once, and divided by pi seconds. So I'm getting, and I want to make sure I did that right. So 9.8 times 60 times 60. Okay. Divided by 4, divided by pi, divided by pi, 894. So the length is 894 meters. And on the moon, now, it's going to be 9.8. Actually, the moon is 1.6 meters per second squared times 60 squared all over 4 pi squared. So it'll be 146. There we go. All right, and we've already done that problem, so we're good. All right, well, one thing I do want to mention is that when you look at the period of a spring, turns out that the period is equal to 2 pi square root of k all over m. And for a pendulum, so what this tells me is that the period and the frequency of a pendulum has nothing to do with its mass. So when we build buildings, so like these really tall skyscrapers, they tend to wobble with the wind. They resonate with the wind and they vibrate back and forth. So, and they tend to act like a spring. Actually, they don't. They tend to act like a pendulum. It doesn't matter how many people are inside this building, they're going to oscillate at the exact same rate because they're acting like a pendulum. That's actually pretty cool, because imagine if you had a building that was full of thousands of people and the period got shorter, so that means the frequency gets faster. It would be terrible, right? If you had your building completely full of people and it made it vibrate more, it would be a horrible thing. So you don't want that to happen. So when we model, the reason why we study simple harmonic motion is because the way materials behave, at the atomic level, they behave like springs, but when you start putting them together, they behave like pendulums. And that helps us with the research that we do on strengths and materials of substances that we use to build those things.